suppose you need to integrate something that looks like this. Your first thought would be a u substitution, but go ahead and try it, and you're going to quickly see that u substitution simply won't work. So, I mean, that creates a problem, and the way that we get around this problem is a technique called partial fractions. Now, suppose I ask you to integrate something that looked like this. Integral of 1 over x minus 1 over x minus 1 dx. That you would kind of snicker at and say ain't no big deal. That's just ln x minus ln of x minus 1 plus c. But notice that if I take 1 over x minus 1 over x minus 1 and I perform this operation of subtraction, x times x minus 1 is the least common denominator. That gives me x minus 1 minus x over x times x minus 1, which is this negative 1 over x squared minus x. That is what we start off with over here. So there's got to be a way that if I can perform this operation of subtraction or addition and get a single rational function like this, then there must be a way that I can take that rational function and go backwards, go back to get to this. That is what the idea of partial fractions, or commonly are often referred to as partial fraction decomposition, is all about. So let's walk through this with the basic idea, and then we'll kind of step by step explain what needs to be done. So first of all, I need my denominator to be easily factorable. If I can't factor this, then it's going to fall apart on me. This factors very nicely to x times x minus 1. Now I'm going to write as a sum of factors. I know that if I had two fractions that I added together, that multiplying them, the denominators, gave me this denominator. So I'm going to break this up. Here's a linear term. Here's another different linear term. So one of them is going to end up here. The other is there. Now, I don't know what these coefficients are going to be like in the numerator, so I'm just going to list them as a and b. Now that I have it set up like this, all I have to do is solve for a and b and then integrate. So the question is, how do I solve for a and b? Well, negative 1 over x squared minus x is equal to some constant over x plus some other constant over x minus 1. Notice if I multiply through, if I multiply both sides by x squared minus x in this case, well, let me rewrite that. I think I want to write it as x times x minus 1. That's the same thing, right? When I distribute it, it's going to cancel here and leave me with an x, so I'm going to end up with a bx. And over here, the x are going to cancel, so I'm going to end up with a times x minus 1. And over here, I'm going to end up with just a negative 1, because all of this will cancel with this. So now I have it set up in an equation that I can actually solve. So if I let x equal 1, I chose 1 because that's going to give me a 0 right here. Then all that's left is negative 1 being equal to b times 1, or b in this case equals negative 1. So now I know the value of this coefficient right there. So now I know that b is equal to 1. What if I go ahead and let, I'll say x equals 0? I could have picked like 2 or something if I wanted to, because I know that b is 1. b is already solved for, so I could have picked any other number. But x equals 0 is kind of nice. That makes the b go away, and I get a negative 1 on the left equals a times, well, x is 0, so a times negative 1. That's negative 1 equals a negative a. That implies that a must be equal to 1. So now that I have that, I can go ahead and integrate. So the integral is going to be, let's see, a over x, a was 1, 1 over x, plus b was a negative 1, so I'm going to bring the negative down just to make it a minus 1 over x minus 1 dx. And that's the same integral that I did earlier. So this is the basic idea behind applying partial fraction decomposition to this first example that we looked at a moment ago. So let's go ahead and take a look at some steps. First of all, if this original function that we're trying to integrate, use substitutions, other stuff don't seem to work, if it's an improper rational function, then I'm going to divide it out. This will give me a polynomial plus a proper rational function. So the polynomial I can easily integrate. That's not a big deal. So I'm going to take this proper rational function and factor the denominator. If I have to, it may be, well, I will probably have to. It could be that I end up with something that I can just go ahead and integrate right away. Maybe a use substitution will work now. But you're probably going to have to factor the denominator. If it's not an improper rational function to begin with, then you start off right here with the idea of factoring the denominator. Now, for each linear factor of the form px plus q to the m, like x plus 1 cubed or 2x plus 3 to the fifth, something like that, for each one, the decomposition must include the sum of the m factors. So, if it looked like this, x plus 1 cubed, in this case p and q are both 1, what this is saying by the sum of the factors is that I'm going to have an a over x plus 1, see this is a linear term, x plus 1, plus a b over x plus 1 squared plus c over x plus 1 cubed. So what they're saying is because I have this linear factor cubed, I'm going to have it here, and the lower, well, it's not really lower terms, but it's going to be the sum of the lower factors. So I'm going to have 2 and to the first. If this was to the fifth, I'd have a constant over x plus 1 to the fifth, a constant over x plus 1 to the fourth, all the way down to a constant over x plus 1 to the first. Now, if I have quadratics of the form ax squared plus bx plus c to the n, I must include the sum of the n fractions, just like we did here, and it also includes the lower terms of x. Well, that may seem kind of confusing. So what that is saying is using this and just using n, this would look like ax plus b over ax squared plus bx plus c plus cx plus d over ax squared plus bx plus c squared plus yada yada yada, following that same pattern out here somewhere to I'm going to change these coefficients here real quick just to make it a little bit easier. I'm going to call this b1 and c1 and make this b2 and c2. That gives me down here bnx plus cn over ax squared plus bx plus c to the n. So if this was cubed, this would be a 3, this would be a 2, this would be a 1, just like it is. And these b's, these b1s, c1s, notice when I talk about the lower terms, before it was just a constant. If I have a linear function, if I think of derivative of a linear function, that's just a constant, is one lower term, so to speak. Here, if I have a quadratic, if I take a derivative of a quadratic, I end up with a linear function. So I'm going to have a linear function up here. If this was a cubit, the derivative of a cubit is a second degree polynomial, a quadratic. So I end up with a quadratic here with all those lower terms. So now that I have this set up, just like I did before, all I need to do is solve for a, b, and c. Once I have a, b, and c solved, I can go ahead and actually integrate.